Hello, we are Group 3, and we're going to be presenting on the Baltic Sea hypoxia problem. Here's a little bit about us and our majors. So first we need to consider the background and geography of the Baltic Sea. The Baltic Sea is an arm of the Atlantic Sea located in northern Europe, and it's the world's largest inland body of brackish water, meaning it's part saltwater and part freshwater. It receives about 447 kilometers cubed of deep saltwater inflow from the North Sea, and the remainder comes from rivers and streams and freshwater. And in terms of outflow, about 940 kilometers cubed of brackish water flow into the North Sea. And as you can tell by this image, it's very isolated from the rest of the Atlantic and the North Sea, with the only passing point being the Danish Straits by Denmark. Inflow into the Baltic Sea is very sporadic, and its salinity and oxygen levels depend on major Baltic inflows, which only come about 10 years at a time. The last one was in 2014 and was the third largest ever recorded at 198 kilometers cubed of saline water. Hypoxia is defined as the lack of oxygen dissolved in a body of water at around less than 2 milligrams per liter for our purposes, and anoxia is the complete loss of oxygen. The Baltic Sea, due to its limited connectivity to the Atlantic, has always been historically prone to hypoxia, but a recent trend in the past century has indicated that human-caused eutrophication has made the hypoxia problem much worse. In 2018, the hypoxic area was about 70,000 kilometers squared, making the Baltic Sea the largest human-caused dead zone, about roughly the size of Denmark. Here's a map of the hypoxic zone over the years, and as you can see, it's greatly increased, especially in the deeper waters in the middle of the sea. So the main difference between the previous hypoxic periods and the current one is human-induced eutrophication. And as you may already know, eutrophication is the result of excess nutrients making their way into a body of water. In this case, nitrogen and phosphorus wind up in the Baltic, resulting in massive blooms of algae, known as phytoplankton, that happen in warmer months. When the algae die, they sink to the seafloor, where they're decomposed by bacteria that consume a lot of oxygen in the process. This process, when repeated year after year, leads to massive dead zones that can't support marine life. Other notable dead zones that you might have heard about include those in the Gulf of Mexico and the Chesapeake region.
Impact of climate change on hypoxia. Rising sea levels associated with increasing annual average temperatures are increasing the water volume. This increases the overall volume of shallow coastal water susceptible to hypoxia and promotes stratification of the water column that is in turn set the stage for low oxygen in bottom waters, particularly in bays with stills. Increased temperatures and changes in seasonality associated with climate change are predicted to extend the duration of seasonal hypoxia in areas of the Baltic, approximately doubling the hypoxic season by the end of the century. Changes in the frequency and intensity of precipitation expected with climate change will influence dead zones through nutrient delivery to coastal waters and changes in water column stratification. Impact of overfishing on hypoxia. Overfishing of Baltic cod has intensified the issue of hypoxia in the Baltic Sea. Codfish eat sprats, which are small species that eat microscopic zooplankton, which in turn eat algae. Fewer cod and more sprats mean more algae and less oxygen. Impact of nutrient runoff on hypoxia. Hypoxia occurs in coastal waters that receive high loadings of nutrients from anthropogenic sources. Runoffs from farms typically contain high levels of nutrients, particularly nitrogen and phosphorus, which flows into larger bodies of water and eventually the oceans and stimulates algal growth. Warming also produces stratification, where the water separates into layers based on temperature or salinity, creating a physical barrier that prevents oxygen from reaching the bottom of the sea.
Alright, so first off, we have the impacts that the hypoxic zones have on recreation and tourism. The algal blooms caused by the nutrient runoff can be toxic to humans, which affects their ability to do things like boating, swimming, and fishing, as well as a loss in tourism revenue for the countries bordering the Baltic Sea. I cannot find any specific statistics on the Baltic Sea, however, a similar hypoxic zone in the Black Sea led to a $500 million loss in tourism revenue every year. As well as beaches can be closed due to the effects of toxic algae and cyanobacteria. And as you can see on the right there, these algae and algal blooms wash up onto beaches and cause the waters to be cloudy and be dangerous to humans. Alright, next we have the local economic effects. So the reduction in things like tourism, commercial fishing, results in a 3.8 to 4.4 billion euro loss annually in nations around the Baltic Sea. In the graph on the right there, you can see the total annual loss per person per country in the Baltic Sea. Countries like Sweden, Finland, and Denmark bear the brunt of the damage to their economies. In Sweden alone, the economic benefit of reducing eutrophication is estimated to be over 70 billion Swedish krona, or 10 billion US dollars per year just in Sweden alone. And that's because these hypoxic zones drastically impact commercial fishing, tourism revenue, as previously stated. There are fewer large fish for commercial fishing operations to be able to actually keep. You have an increased proportion of smaller sized organisms that don't have any economic value, and species such as Baltic cod, which are one of the major exports in the Baltic region, are very drastically impacted by the hypoxic zones, and there are less of them and they're smaller, which causes there to be less incentive to harvest these fish. And finally, we have the effects on aquatic wildlife in the ecosystem. Algal blooms, as previously stated, block out the sunlight to seaweed and other bottom-dwelling organisms, which reduces the habitat and disturbs the breeding ground for fish like pike, perch, and other species, which leads to drastically reduced reproduction rates. Furthermore, fish miss out on 106,000 metric tons of carbon in fish food per year due to bottom-dweller organisms dying out from oxygen deprivation and reducing the amount of available food for these fish. Finally, cod, which are one of the most important and one of the most valuable fish in the Baltic Sea, are more likely to be caught with empty stomachs near these hypoxic zones. And overall, the body condition of cod is down 30% since 1990, which includes their length, width, weight, and overall economic benefit. On the right side of the screen here, you can see that there is a bunch of dead fish. This is the result of a fish kill in Urstromen, Finland in July of 2015. Fish kills are when a sudden change in the oxygen levels, such as a sudden bout of hypoxia, causes a large amount of fish to die and be washed up on the beaches and in the areas around the hypoxic zone.
Because hypoxic zones are such a long-term issue and their damage isn't always prioritized by the public, there are relatively few solutions regularly implemented. Baltic Sea 2020 is an organization in Sweden that aims at reducing the Baltic Sea hypoxia by the end of this year. In fact, one of their projects in the past decade has been to control the eutrophication and growth of algal blooms through biomanipulation by increasing the number of predatory species. These fish, specifically pike perch, consume zooplankton feeders such as herring, increasing the zooplankton population, which reduces the amount of algae. 870,000 pike perch were released over a period of 4 years, according to the Baltic Sea 2020 website. But unfortunately, this particular project was not effective in increasing pike perch population over time. It had little effect on the food chain and trophic system, and therefore little effect on the algae levels. A high level of phosphorus is beneficial for algal blooms, therefore making the chemical removal of phosphorus the most immediate action that can be taken to reduce the size of hypoxia. The idea behind the term chemical removal can be more accurately defined as the inactivation or binding of phosphorus with substances such as aluminum. The Baltic Sea 2020 even organized a project in the Grand Bay off of Sweden, investigating how iron may be more effective for phosphorus binding than aluminum in more shallow waters. Other chemicals have been used as well. In fact, this method is not new. A 2009 issue of Environmental Science and Technology even notes the danger that some of these chemicals pose to sea life if binding is ineffective. The previously mentioned solutions focus heavily on reducing the size of hypoxia by directly managing the factors of harm such as algal blooms and nutrient concentrations. But with the many innovative minds working in our society today, some are choosing to take a more contemporary approach. To understand these newer ideas, it is important to take a look at the issue of stratification. The Baltic Sea is permanently stratified due to its natural mix of freshwater and saltwater. Stratification does not allow oxygen to reach the deeper levels of the seawater, which causes these dead zones to occur, making the Baltic Sea more susceptible to hypoxia. This video demonstrates the lack of mixing that occurs, leaving the more oxygenated waters at the surface. Architect Adam Novotny designed a structure that he proposed could mix waters of stratified salinity in order to oxygenate the deeper levels. Though backed by less research and scientific experimentation, the architect looked at this problem from a new angle and could be very promising in the future if infrastructure and natural ecosystems allow it.